This section covers an introduction to the types of surface which need to be cleaned and an explanation of the cleaning techniques shown here. New unpainted steel is relatively easy to clean. Provided that the surface has not been exposed to corrosion in a chemical or marine environment, the biggest problem is likely to be removal of mill-scale deposits. Blast cleaning using either shot or grit can easily remove most mill-scale. An advantage of using grit for blasting is the simultaneous creation of an angular surface profile that is suitable for good adhesion of coatings. Tightly adhered mill-scale can be difficult to remove without blast cleaning. New unpainted metals such as aluminium or zinc can be prepared by light blast cleaning to both clean and roughen the surface. Adequate adhesion of coatings to the prepared surface may be difficult to achieve any other way. Chemical or solvent cleaning may be possible, but special paint primers, such as acid etch primers, must then be used to achieve good performance. Mill-scale is formed by reaction between the hot steel and oxygen in the environment during the production process. As a result, the surface of newly produced hot-rolled steel is generally covered with blue-black deposits of mill-scale. The adhesion of mill-scale to steel is unpredictable and may vary from tightly adherent to lightly adherent. If the mill-scale is over-coated, failure of the coating can occur due to delamination of the mill-scale from the steel surface. Mill-scale is also relatively smooth, a factor which is significant for today's high-build, fast-drying coatings. Adhesion of coatings to smooth mill-scale may be poor, resulting in failure through loss of adhesion. Mill-scale is cathodic relative to bare steel. When steel is partially covered in mill-scale and exposed to corrosion, the cathodic mill-scale does not corrode, being protected by the anodic steel. Corrosion does take place at the anodic surface, and base steel is lost. This effect is the opposite of what is generally required. When most of the surface is covered by mill-scale, corrosion at the anodic areas may be accelerated by the unfavorable area effect shown in the formula. For best results, new steel should be cleaned by abrasive blasting to remove mill-scale and to provide an anchor pattern for optimum coating adhesion. Surfaces that have been exposed to the environment and have subsequently corroded may be more difficult to clean. The surface is often rough and may have deep pits and other irregularities. When chemical contaminants have become bonded to the surface through a chemical corrosion reaction, removal may require special treatment. The processes used for cleaning corroded steel are generally the same as those used for cleaning new steel, and include hand and power tools, blast cleaning, and perhaps water jetting. Zinc exposed to the atmosphere develops a passive film of zinc oxide and/or zinc carbonate. Provided they are tightly adherent, these layers can aid the adhesion of paints due to their relative roughness. Loosely adherent or powdery salts should always be removed before painting. Water washing may be effective at removing most loosely adherent zinc salts, provided a pressure wash technique is used and plenty of clean fresh water is available. This technique is less effective than blast cleaning. Zinc surfaces should be lightly blast cleaned, brush blasted, to roughen the surface prior to painting, or treated with an acid-based solution, for example, acid etch primer or acid wash solution, to provide a clean surface with a profile. Either of these treatments will enhance coating adhesion to the substrate. Current thinking suggests that better results are obtained by blast cleaning before coating rather than relying on etch primers to provide good adhesion. Oil-based coatings, such as alkyds or epoxy esters, perform poorly when applied over galvanized or zinc-coated surfaces because of a reaction between the coating and the zinc surface called saponification. This reaction, the formation of soap, causes degradation of the oil-based binder and consequent loss of adhesion of the coating to the zinc surface. Aluminium oxidizes in the atmosphere much like zinc and zinc-coated surfaces to form a passive film of aluminium oxide. The surface should be lightly blasted or wire brushed to remove powdery or loosely adherent salts before treatment with an aluminium treatment, for example, etch primer before coating. A primer with known compatibility and strong adherence to the clean surface should be selected. Other surfaces that are commonly painted include plastics, wood and concrete. All of these require special surface preparation and coating suited to their special characteristics. A discussion of surface preparation for these surfaces can be found in the Advanced Surface Preparation module. The choice of surface preparation method is often determined by the choice of coating system. Coatings should be matched to the degree of surface preparation desired or possible. If coatings are to be successful with very little surface preparation, they must be chosen for their surface-tolerant characteristics. Most coatings need better standards of surface preparation. Modern high-performance coatings are likely to require blast cleaning to a high degree of cleanliness, and in some cases may also require that the surface is free of chemical contamination. The degree of cleaning required is closely related to the type of coatings to be used, although in general a better standard of cleaning will provide better long-term protection from any coating system. Solvent cleaning is a method for removing all visible oil, grease, soil, drawing and cutting compounds, and other soluble contaminants from steel surfaces. It is intended that solvent cleaning be used prior to the application of paint and in conjunction with surface preparation methods specified for the removal of rust, mill scale or paint. The standard SSPC SP1 is the only commonly used standard that formally governs solvent cleaning to remove oil, grease, dirt, soil, drawing compounds and other similar organic compounds. SSPC SP1 defines a variety of pre-cleaning methods, including those listed here. Organic solvents such as kerosene, turpentine, naphtha, mineral spirits, toluol, xylol, etc. clean the metal by dissolving and diluting the oil and grease contamination on the surface. Some organic solvents used for solvent cleaning may be considered hazardous to health and are generally likely to be a fire risk. In particular, toluol is subject to health and safety restrictions in many countries. Inorganic materials such as chlorides, sulfates, weld flux and mill scale are not removed by organic solvents. The last wash or rinse should be made using clean solvent to remove the slight film of oil or grease that may be left on the surface. This film, if left in place, may interfere with the adhesion of the coating to the surface. Some solvents, for example xylol and toluol, will also dissolve some paint films so they can be removed from the surface. Non-convertible coatings, for example chlorinated rubber or vinyl, are most likely to be softened or removed by solvent washing. Petroleum-based mineral spirits with a minimum flash point of 100 degrees Fahrenheit, 38 degrees centigrade, may be used as a general-purpose solvent under normal conditions. In hot weather, 80 to 90 degrees Fahrenheit or 28 to 32 degrees centigrade, high flash point mineral spirits with a minimum flash point of 120 degrees Fahrenheit, 50 degrees centigrade should be used. All solvents are potentially hazardous and should be used when their concentrations in air being breathed by workers are low enough for safety, in accordance with current federal, state and local regulations for threshold limit values, TLV. Appropriate fresh air masks should be used in confined spaces and when the safe concentration may be exceeded. The fresh air supply should be free of carbon monoxide, CO, or other contaminants from other sources such as engine exhausts, etc. The concentration of solvents in air should not exceed the lower limit of flammability, known as the lower explosive limit, LEL, or a fire or explosion could occur. Such concentrations are most likely to occur in confined spaces, such as tanks, pipes or vessels. In general, cost considerations and regulations restricting the use of organic solvents have become so stringent as to discourage the use of these materials except in highly controlled special situations. Alkaline cleaners such as trisodium phosphate, TSP, and sodium hydroxide saponify certain oils and greases, and their surface active components wash away other contaminants such as oils. These cleaners may also saponify certain coating vehicles, and the soaps formed can be washed away easily with water. Often, alkaline cleaners are combined with surfactants, wetting agents, inhibitors and detergents to form proprietary products and should be used according to the manufacturer's recommendations. These products are often used at elevated temperatures. In the cleaning process, a slightly soapy film may be left on the surface. This film must be washed off, usually with a high-pressure, hot water rinse. Residues that remain on the surface will affect the adhesion of the coating to the metal. A pH paper test could be made to determine the effectiveness of the wash. In general, the pH of the washed surface should not exceed the pH of the wash water. In some cases, the owner may elect to use an acidic wash, such as 0.1% by weight chromic acid, sodium dichromate, or potassium dichromate, to neutralize traces of the alkali on the surface. Safety precautions should be followed in using the alkaline cleaners and chromic acid. The alkaline materials may cause burns, and the chromic acid and chromates may cause dermatitis. Workers should wear rubber gloves and safety goggles or eyeglasses, and where these materials may be applied by spraying, respirators should be used. Acidic cleaners are usually composed of fairly strong acids, such as phosphoric acid, H3PO4, with small quantities of surfactants, water-miscible solvents, and organic wetting and emulsifying agents. Acidic cleaners remove soil by chemical attack and by dissolving the reaction products. They may be used to remove corrosion products and for other special purposes. Disposal of alkaline or acidic cleaners is often a problem, and collection of the waste or used materials is essential. Used materials cannot be washed into the normal drainage system or allowed to run off into the general water system. Detergents. Increasingly strict regulations regarding the use of organic solvent and the safety considerations in using alkaline or acidic cleaners have led to an increased use of detergents, especially the biodegradable types, in the removal of oil, grease and other similar contaminants from the surface. Generally, these cleaners are composed of buffering salts, dispersants, soaps and inhibitors, and they function by wetting, emulsifying, dispersing and solubilizing the contaminants, which can be washed away using water, usually hot, or steam. They are frequently used at temperatures ranging from 150 degrees Fahrenheit to 212 degrees Fahrenheit, 65 degrees centigrade to 100 degrees centigrade. Emulsion cleaners typically are proprietary products and should be used in accordance with the manufacturer's instructions. These cleaners may contain oil-soluble soaps or emulsifying agents, buffering salts, dispersants and inhibitors, along with kerosene or some type of mineral spirits. Emulsion cleaners are generally sprayed onto the surface to be cleaned, and they function by wetting, emulsifying, dispersing and solubilizing the contaminants. Generally, the emulsion cleaners on the surface leave a thin film of oil which must be washed away with hot water, steam, solvents, detergents or some type of alkaline cleaning agents. Water is a common, if not powerful, solvent and may be used to good effect in cleaning a surface. We'll discuss its use later when we discuss water blast cleaning and water jetting. In the use of any cleaning method, appropriate safety precautions must be taken. Also, it's important to thoroughly rinse surfaces, particularly when alkaline or acidic materials are used, to minimize the amount of soil remaining and to remove residues of cleaning materials that could adversely affect subsequent coating performance. Hand tool cleaning is a method to prepare steel surfaces by the use of non-powered hand tools. Hand tool cleaning removes all loose mill scale, rust, paint, and other detrimental foreign matter. It's not generally intended that adherent mill scale, rust, and paint be removed by this process. Mill scale, rust, and paint are considered adherent if they cannot be removed by lifting with a dull putty knife. A standard which is commonly used to control the hand tool cleaning process is hand tool cleaning SSPC SP2. This is comparable to ISO 85011 ST2 or ST3. SSPC Viz 3, ISO 85011 or other visual standards of surface preparation agreed upon by the contracting parties may be used to specify the surface finish required or to verify the condition achieved. Both standards define the use of a dull putty knife to determine whether contaminants are firmly adherent or not. Note, some inspectors have been known to use a sharpened putty knife, which violates the standard. Tools used in hand cleaning include wire brushes, scrapers, chisels, knives, and chipping hammers. When hand tool cleaning operations commence, certain procedures are followed. The surface is inspected to determine its condition and the presence of heavy layers of rust, and to detect any foreign substances such as oil, grease, or dirt. Solvent emulsion cleaning may be specified or required to remove oil, grease, or dirt. Heavy layers of rust should be removed by chipping. The surface is cleaned with any of the hand tools previously mentioned and then inspected prior to coating. The coating should be applied within the time period required by the specification. Manual cleaning is the slowest and perhaps the least satisfactory method of surface preparation. Normal tools used are wire brushes or scrapers or chipping hammers. The process is slow, labor-intensive and costly, with the end result still far from satisfactory. It is practically impossible to remove all rust and mill scale by this method. A complicating factor can be the reluctance of labor to engage in arduous manual tasks. Slow progress and deteriorating labor relations can lead to significant increases in the cost of achieving a clean surface by these methods. Hand tools have the advantage of being portable and not requiring support power supplies. They're most suitable for use when small areas of work are to be prepared in the vicinity of other workers, or when access is difficult, such as when maintenance is performed on communication towers, 100 meters in the air. Manual cleaning should only be used when weather or some other factor precludes the use of another, more efficient process. Hand cleaning is one of the oldest methods of surface preparation. Generally, it's used only when power-operated equipment is unavailable, where the work is inaccessible to power tools, where the job is too small to warrant use of power tools. Power tool cleaning is a method of preparing steel surfaces by the use of power-assisted mechanical cleaning tools. These tools are essentially similar to the tools used for hand tool cleaning, but a power source such as electricity or compressed air is used. This process can remove all loose mill scale, loose rust, loose paint, and other detrimental foreign matter, but is not intended to remove adherent mill scale, rust and paint. As in SSPC SP2, mill scale, rust and paint are considered adherent if they cannot be removed by lifting with a dull putty knife. The standards most commonly used to govern the power tool cleaning process are SSPC SP3 or ISO 8501-1ST3. Power tool cleaning is frequently used in maintenance operations. In addition to removing loose mill scale, rust and paint, this method is used to remove weld flux, weld spatter and laminations, and to smooth rough welds, and round out gouges before abrasive blast cleaning. The machine design is of two general types: straight or inline, or vertical or right angle. Shown here is a right angle wire brush. Overworking the surface with a wire brush may be detrimental because excessive burnishing develops a polished surface which provides a poor anchor for most coatings. Rotary power wire brushes can also easily spread oil and grease over the surface. Therefore, solvent cleaning is an essential step before power wire brushing. Problems with polishing the surface rather than providing a roughened surface are particularly likely with this technique, and mean that the use of rotary wire brushes is considered to be less desirable than other forms of power tool cleaning. A chipping or scaling hammer is the most widely used type of impact tool. A chisel is inserted into the power tool, and the impact from an air-operated or electrically operated piston is transmitted to the chisel, and in turn to the surface to be cleaned. Chisels may be of different shapes and materials. They should be kept sharp, otherwise they may drive rust and scale into the surface. Scrapers and special chisels can be suitably mounted into pneumatically or electrically powered impact tools. Scaling or chipping hammers are generally a slow, costly method of cleaning the surface, but in some cases, such as when considerable rust, scale or heavy paint formation must be removed, they prove to be economical. Great care must be exercised in using these tools because of the tendency to cut into the surface excessively, removing sound metal and leaving sharp burrs where the paint will fail prematurely. A needle gun or needle scaler consists of a number of hardened steel rods which are vibrated against the surface. It is slow in operation and suffers from the same problem as other power tools, since it has a burnishing effect when producing a relatively clean surface. It does, however, produce a surface profile. The needle scaler is effective on welds, corners and irregular surfaces. Certain types of needle scalers fitted with vacuum devices are being used to remove lead-based paint to comply with federal regulations regarding lead abatement. Piston scalers operate similar to scaling hammers, but the piston also acts as an impact tool. A hammer piston, which takes the place of the chisel, is a circular shaft with the cutting end cross-shaped, somewhat like a star chisel. These scalers are available with 1, 2 or 3 pistons operated in one tool. Also, large assemblies with as many as 15 pistons are available for use on flat, horizontal surfaces such as steel decks. A wide variety of chisels are available for different types of work. These tools can be used advantageously on large areas to remove rust and scale. Care must be exercised to prevent the cutters of these large rotary scalers from cutting the metal to such an extent that metallic points extend far above the surface, causing early paint failure due to insufficient paint coverage. If these tools are used to remove mill scale and rust from the surface, it's very likely that the surface will be very rough, and care must be taken to ensure that all peaks of the anchor pattern are covered by the coating applied. Grinders and sanders are often employed to prepare surfaces for painting. Machines used for this purpose may be the same as those used for power wire brushing, with suitable sanding discs or grinding wheels substituted for the wire brushes. The abrasive grit size used with this type of cleaning equipment must be selected properly. Too coarse an abrasive will create a deep anchor that may be unsuitable for good paint performance. An abrasive that is too fine may cause early clogging of the grinding wheel or sanding disc, thus making the process inefficient. Grinding is well suited for removing weld spatter, for smoothing weld seams, or for rounding off sharp edges or corners. Grinders are frequently used in repairing minor fabrication defects. The anchor profile produced can be extremely good, with complete removal of rust and mill scale. However, such methods of cleaning are very expensive for large areas. Also available are pneumatic and electrically operated sanders that have a flat pad or abrasive surface in contact with the metal to be cleaned. Some of these motor-driven sanders have an orbital motion. Flexible shafts are used on a small scale to operate rotary wire brushes and grinding wheels. On other grinding equipment, the discs or wheels are mounted directly to the main shaft of the motor of other portable or stationary units. In 1989, SSPC adopted a new standard, SP11, titled Power Tool Cleaning to Bare Metal. When the highest levels of surface preparation are required or specified, for example, SSPC SP11, production of a surface profile is a mandatory part of the surface preparation operation. A surface profile can also be achieved using special power tools designed for the purpose. SSPC SP11 calls for power tool cleaning to produce a bare metal surface and to retain or produce a profile, where a clean, roughened bare metal surface is desired, but where abrasive blast cleaning is not feasible or is not allowed. Metallic surfaces prepared according to SSPC SP11, when viewed without magnification, shall be free of all visible oil, grease, dirt, dust, mill scale, rust, paint, oxide, corrosion products, and other foreign matter. Slight residues of rust and paint may be left in the lower portion of pits if the original surface is pitted. If painting is specified, the surface must be roughened to a degree suitable for the paint system, with a profile not less than 1 mil, 25 microns. Power tool cleaning in accordance with this standard produces a greater degree of cleaning than SSPC SP3. However, surfaces prepared according to SSPC SP11 should not be considered equal to surfaces prepared by abrasive blast cleaning. Although this method produces surfaces that look like near white or commercial blast, they are not necessarily equivalent to those surfaces produced by abrasive blast cleaning. Some of the suitable tools and media used to achieve surfaces according to SSPC SP11 are shown here. While quicker than using hand tools, the work is still labor-intensive and relatively expensive. Removal of rust and other contamination from the bottom of pits and irregularities in the surface is very difficult. In response to increased environmental regulations, many power tools have been produced with vacuum recovery systems designed to collect any dust, particularly old paint, generated by the cleaning operation. A major disadvantage to the use of power tools is the burnishing effect likely to be produced on the metal surface. This polishing effect, inherent with power tools, is the most unsatisfactory feature of this method. A polished surface affects the quality of paint adhesion, and the effect should be avoided if at all possible. The most generally established method of surface preparation for the application of coatings is by dry grit blasting, as defined below. Indeed, when modern sophisticated coatings are applied for surface protection, there is no truly satisfactory or economically equivalent alternative process. The fundamental principle of the grit blasting process is the removal of rust, mill scale, or other surface contaminant, and obtaining a suitably roughened surface by projecting a highly concentrated stream of relatively small abrasive particles at high velocity against the surface to be cleaned. The surface is abraded through the high-velocity impact of abrasive particles. In preparing steel surfaces for painting by blast cleaning, rust, mill scale and old paint are removed along with some of the base metal. Various degrees or standards of surface cleanliness achieved by abrasive blast have been defined. The abrasive blast cleaning standards for new steel most commonly used in abrasive blast cleaning applications are produced by NACE, SSPC or ISO. In October 1994, NACE and SSPC issued the following joint surface preparation standards for abrasive blast cleaning. NACE number 1, SSPC SP5, white metal blast cleaning. NACE number 2, SSPC SP10, near white metal blast cleaning. NACE number 3, SSPC SP6, commercial blast cleaning. NACE number 4, SSPC SP7, brush-off blast cleaning. These standards are roughly equivalent to the ISO standards that were developed from the original Swedish standards. ISO 85011 was published in 1988 and contains 4 standards. SA3, blasting to visually clean metal. SA 2.5, very thorough blast cleaning. SA2, thorough blast cleaning. SA1, light blast cleaning. Each system of standards represents a progressive scale of visual appearance only, the best grade being shown first in each case. The quality of blast cleaning is determined visually, and photographic standards are generally used for comparison purposes. There is no correlation between the degree of blast cleaning used and the surface profile produced, and no specific correlation with removal of chemical contamination or non-visible salts. For these issues, other standards and measuring techniques must be used. Particles of abrasive may be projected by direct feed of the particles from a pressurized container into a high-pressure airstream, pressure blasting, or by centrifugal projection from rapidly rotating impellers, centrifugal blasting or airless blasting. This is the most commonly used method of abrasive blasting. Abrasive is forced under pressure from the pressure vessel, blast pot, through the blast hose. It is a high production method used for heavy-duty jobs, for example in shipyards, refineries and chemical plants, and for cleaning railroad cars and buildings. With this unit, material is blasted forward and recovered immediately by a vacuum. This method is used when no abrasive can fly around, for example, near sensitive equipment. This blasting method is expensive and is used only in special situations, such as in removal of lead-based paints. Air moves sand from hopper to nozzle. No pressure is applied to the blast hopper. Energy to move the abrasive out of the hopper comes from a reduction of air pressure through a venturi. Because abrasive moves forward at a lower velocity, this method is used for light-duty jobs, such as frosting glass, blasting welds, and blasting car bodies and touch-up work. Abrasive is blown into a standpipe and out through an elbow into the hose. This method is commonly used with fine abrasives. A suitable type of blast unit must be chosen for the specific job. The most commonly used manual blast units are pressure vessels and are able to deliver abrasive into a compressed air stream by pressurizing the abrasive container. Other designs, such as gravity-fed pots or suction-fed units, are not commonly used for surface preparation on an industrial scale. When control of dust and debris is important, vacuum recovery systems are fitted to existing equipment, or specially designed units are used. The abrasive and waste are collected together, then generally separated and the abrasive recycled. The abrasive used in this case must be suitable for recycling. The size of blast unit usually varies with the job. Blast units can range in size from those holding 1.5 bags of abrasive for a small job to those holding over 40 tons of abrasive. It is important to document the quantity, type and size of equipment on the job. If the specification addresses certain equipment requirements and the equipment does not meet these requirements, the inspector should report the deficiency to the owner's representative. It is sometimes desirable to blast clean individual items in an enclosed space so that other trades can continue to work in the immediate vicinity. If this is a regular requirement, many factories will buy or build a blast cleaning cabinet. The size of typical cabinets may vary from the very small cupboard, where blasting is done from outside the cabinet, with hands inserted through holes in the side, to the relatively large blasting room. The more sophisticated blast rooms may have a rail system to transport large items into the blasting area, and will have grit recovery and recycling systems. In general, the blast cleaning apparatus is similar to that used for on-site blasting. The most complex of the blast cleaning cabinets are designed for large quantities of steel to be blast cleaned on a regular basis, such as all plate received by a shipbuilding yard. These machines, often known as wheelabrators, are designed to work on a continuous basis and include a conveying system that will carry items through the cabinet continuously. It is usual for these cabinets to use a system of rotating wheels with vanes to propel the abrasive, from which the term wheelabrator has been adapted for general use. These cabinets too have an abrasive recovery and recycling system and are capable of very high rates of cleaning. Blasting with a wheelabrator machine is often highly automated and is best suited to repetitive blasting tasks at a fixed location. Typical locations would include shipyards or steel structure fabrication facilities, such as those used for building oil production platforms and their ancillary equipment. This method of cleaning is used in a stationary setup when work can be brought to the equipment, for large flat surfaces when a portable wheel blast unit can be driven across the surface, such as on the flight deck of an aircraft carrier, or on concrete surfaces such as floors, pits, etc. To eliminate the need for compressor setup, including air blast hoses, abrasive pot and an attendant, and for lower production cost. centrifugal blasting may be used on such workpieces as pipe, piling, reinforcing steel, beams, flat plate, etc., with a series of centrifugal blast wheels housed in a blast enclosure, arranged so all sides of the work are cleaned as it travels through the equipment. Wheel blast operations are described in more detail in the advanced module of this training program. Manual blasting should systematically cover the entire surface to be cleaned by moving the nozzle at fairly constant speeds in straight paths, each succeeding pass overlapping the preceding one and exposing clean metal without any discolored patches. The standard of blast cleaning should be no more and certainly no less than is required by the specification. The nozzle should be held close to right angles to the surface, but at a slight angle so that the abrasive does not bounce right back at the operator. Some surfaces, such as those with heavy mill-scale layers, or with coatings such as thermal sprayed zinc or aluminium, are best blasted initially at a shallower angle, for example 45 degrees. The operator must be aware that this technique, while efficiently removing the existing coating layer, produces a reduced surface profile due to the angle of impact. Final blasting at right angles to the surface is required if the correct surface profile is to be achieved. Speed of nozzle traverse is dictated by rate of cleaning and should be as fast as will clean thoroughly without unnecessary dwell. Hoses are an important part of the blast cleaning process. Two different hoses are used: air supply hoses and blast abrasive hoses. This hose carries air from the compressor to the abrasive blast unit. Generally, the larger the air line, the better. No smaller than 1.25 inches or 35 millimeters inside diameter is recommended. The recommended size should be 3 to 4 times the nozzle orifice. On lines longer than 100 feet, 30 meters, the hose internal diameter should be 4 times the blast nozzle orifice size. The large size eliminates loss of air pressure through the air hose because of friction. There are two types of abrasive supply hose. 4-ply, for use when the hose is subject to external abuse or when there is danger of the operator pulling it at right angles. 2-ply, a lighter hose that is preferred by some blasters because of its greater flexibility. All hoses should have capped ends to allow for coupling and to prevent any moisture or compressed air from working its way through the braid or ply of the hose. Air inside the hose can cause the hose cover to bubble. Water can cause rotting away of the wrapping on the hose. The size and length of abrasive blast hoses are related to their efficiency. Hoses generally cannot be too large. 75% of hoses used today have a 1.25 to 1.5 inch inside diameter, 31 millimeters to 38 millimeters. A rule of thumb is that the hose ID should be 3 to 4 times the size of the nozzle orifice. A whip length of 10 to 15 feet, 3 to 4.5 meters, with only a 0.75-inch ID, 19 millimeter, is sometimes added to the end of the hose for ease of handling. The smaller ID causes a considerable drop in pressure, and it is recommended that operators use a whip attachment only when necessary. Most blast hoses are now manufactured with an internal ground, often achieved by loading the rubber material of the hose with carbon black to allow static electricity to drain to earth. In some situations, an additional external ground may be necessary. Only grounded hoses should be used to ensure operator safety. Only externally fitted couplings should be used. Internally fitted couplings reduce hose ID and reduce the air carrying capacity significantly. In addition, a turbulent condition may be set up at the point where the air and abrasives hit the leading edge of the nipple inside the hose. Pressure drop and heavy wear can occur at that point. Hose diameters should also be of an internal diameter at least 3 or 4 times that of the nozzle bore. All joint seals should be carefully maintained to be fully pressure tight and any leaks quickly rectified. Quick couplings are held in place with external screws penetrating into the wall of the hose. The screws should not penetrate the tube or air leaks can occur. Couplings are made of both bronze, which lasts longer, and plastic, which is lighter and easier to handle when the hose must be lifted into the air. Coupling should be wired shut or otherwise properly coupled, both to ensure safe connections and to prevent the coupling from opening if caught on irregular surfaces. Grounding should be maintained through the coupling. Owing to the inevitable pressure drop within airlines, pressure hoses should be kept as short as possible. When greater distances must be used, the hose should be kept in straight runs, and any bends should be wide and have a smooth radius. Efficient use of the blast pot can save money in both man-hours and abrasives. The blast pot should be emptied daily if practical and kept dry to avoid contamination of the abrasive. Maintenance should be performed to eliminate leaks and eliminate pressure losses. The vessel should be inspected annually and hydro-tested to 1.5 times the design pressure to ensure effective functioning. Blast cleaning is a potentially hazardous operation. Safety with abrasives under pressure is very important. Remember that abrasives and air leave the nozzle at great speed, at a rate close to 450 miles per hour, 720 kilometers per hour, 660 feet per second, or about half the speed of a shotgun charge, and can impact on surfaces or other workers a considerable distance from the operation. The entire system, including hoses, operator and workpiece, must be grounded to prevent injury due to electrical shock. Grounding is particularly important when the operator is working at heights, when shock may lead to a fall, or when blasting in a hazardous environment. In the blast cleaning operation, the air compressor must be capable of delivering sufficient air volume to maintain the required pressure at the nozzle. Related equipment, including the following, must be of sufficient size and type to match the compressor output: air and abrasive hoses, hose couplings, blast nozzles. The compressed air must be free of contaminants, including oil and water. First, since air-supplied breathing equipment is required when abrasive blast operations are being performed, it is critical that the breathing air be fresh and pure. This is the responsibility of the applicator. Second, it is important that the blast air be clean to ensure that the blast cleaning operation does not add contaminants to the surface being cleaned. The blasting contractor is responsible for complying with all requirements of the specifications, such as size of hose, type of nozzle and air volume, when these are detailed in the specifications. The coating inspector may check the requirements to ensure compliance by the contractor. Compressed air is a common source of power for blasting machinery, paint spray equipment, power tools, etc. It is favoured on site because it is relatively safe, being less dangerous than electrical power. In order to produce quantities of compressed air, it is necessary to use a compressor. Normally driven by a diesel motor, though electric compressors are common in fixed workshops, a compressor draws in atmospheric air, pressurizes it, and feeds the air into a pressure vessel known as a receiver. The air is then held in the receiver until demanded by the equipment in use. The production of compressed air gives two problems to the surface preparation process. These are: any change in atmospheric pressure may result in the release of water vapor from the air. Because compressed air in the receiver is stored by pressurizing an oil reservoir, there is a possibility of oil vapor being retained by the air as it is released. Both of these factors require that adequate vapor traps are fitted to blast cleaning equipment in order to remove the contaminating oil and water. Air pressure is measured in pounds per square inch, PSI, or bar. Air pressure is normally set a little above the intended working pressure, a maximum of 100 PSI, 7 bar for portable compressors. This pressure, if successfully maintained, is capable of producing an efficient blast cleaning operation. Adequate pressure is critical to an effective blast process. If the abrasive is not being sent forward at sufficient pressure, much more time is required to accomplish the job. The compressor pressure control should be set to compensate for pressure lost in the blast hose. Pressure at the nozzle can be measured using the hypodermic needle gauge, which we will describe later. Capacity is measured in cubic feet per minute, or liters per minute. The capacity of a compressor will determine the quantity of air it is able to deliver at its working pressure. For blast cleaning purposes, it is better to have a large capacity compressor working below its maximum level, rather than a smaller compressor which is working at or near to its maximum level. The compressor selected should be able to supply more air than is required to allow for reserve capacity for peak loads or for the addition of equipment. For blast cleaning, using a 7/16 inch diameter nozzle operating from one blast pot, it is generally recommended that a compressor with a minimum capacity of 350 cubic feet per minute or 9,900 litres per minute is used. For extended use, a compressor with greater capacity, perhaps 600 cubic feet per minute, 17,000 litres per minute, will operate with less strain and greater efficiency. The same compressor used for blasting is often used to drive air-operated spray guns and other equipment. No other equipment requires such large quantities of compressed air as the blast cleaning operation. It is estimated that with one 3/8 inch, 9.5 millimeter nozzle operating, there will be a 5 pound, 35 kPa drop in pressure for each 50 feet, 15 meters of hose in use. This pressure drop will be compounded according to the number of operating nozzles, the nozzle sizes, and the lengths of hose being used. Another consideration is the size of compressor manifold valve. The compressor should be equipped with outlets of 1.5 inch to 2 inch, 38 millimeters to 50 millimeters, to match the air supply hose. An undersized compressor is a bad investment because of the reasons shown here. A number of accessories are key parts of the compressor equipment. It is essential that surface cleanliness should not be impaired during the blast cleaning process. This can arise from oil vapor or droplets carried over in the air from the compressor, or from moisture entrapped in the high-pressure air, or from residual dust arising during blast cleaning. Precautions should be taken to ensure that compressed air supplies are oil and moisture free. The installation of suitable oil and moisture traps, together with aftercoolers and filters in the airlines, is required, and these must be given adequate maintenance. Most oil and moisture traps are operated with drain plugs in a part open position, allowing accumulated moisture to disperse. Moist air can also cause abrasive to clog in the abrasive lines or blast pot, and may cause rusting of the blast cleaned surface. Filter units contain charcoal and supply purified air to the blast hood. They also are equipped with a monitor to detect the presence of CO, carbon monoxide. The dryer units remove water from the compressed air to prevent the abrasive from becoming wet. Absorbent filters absorb moisture in compressed air to prevent condensation on the workpiece. Refrigerant removes water by cooling air and extracting moisture from the air stream, thereby preventing condensation on the workpiece. Cooler air holds less water than warmer. A centrifugal separator removes water through centrifugal force. A water-cooled heat exchange cools hot air from the compressor, so moisture may be removed from the air stream. An auxiliary receiver or storage tank is sometimes used. It acts as a reservoir of compressed air. The compressed air is fed into the auxiliary tank from one or more compressors until it is needed to power the tools and operations connected to the tank. Compressed air for the blast cleaning operation can be checked for the presence of oil or water by a simple test, which involves the use of white absorbent paper held in the air stream discharging from the compressor. The ASTM D4285 standard test method for indicating oil or water in compressed air requires the use of an absorbent collector, such as white absorbent paper or cloth, on a rigid backing, or alternatively, a non-absorbent collector such as quarter-inch transparent plastic. The collector is centered in the discharging airstream within 24 inches of the discharge point for a period of 1 minute. The test should be conducted on the discharging air as close to the use point as possible and after the inline oil and water separators. The blotter test is used to check visually for any trace of oil or water in compressed air to be used in abrasive blasting or spray application of coatings. In performing this test, the tester should allow the compressed air system to reach operating conditions, allow air to discharge at operating conditions to remove accumulated condensation in the system, fasten the collector material to a rigid backing, avoiding personal contact with the air stream. According to the ASTM standard D4285, any indication of oil discoloration on the collector shall be cause for rejection of the compressed air for use in abrasive blast cleaning, air blast cleaning, and coating application operations. Any indication of water contamination on the collector shall be cause for rejection of the compressed air for use in those applications where water is detrimental, such as abrasive blast cleaning, air blast cleaning, and coating applications. Hydrocarbon oils usually can be distinguished from water using an ultraviolet light, or by detecting the characteristic odor of oil. The surface being cleaned should also be thoroughly inspected for any sign of oil or water. Other factors being constant, the speed of blasting is directly related to the size of the nozzle used. So also is the air consumption. Accordingly, the maximum nozzle size that can be used must depend upon the capacity of the compressor feeding it. The following table shows the volume of air required at various pressures to feed different sizes of nozzles. Maintenance of nozzle size is of considerable importance and can be a problem if normal cast iron nozzles are employed, as these wear over size quite rapidly. More efficient blasting can be obtained by the use of nozzles produced in special wear-resisting alloys or in such materials as tungsten carbide or ceramics. Although of higher initial cost, these nozzles are more economical in practice. The internal profile of the blast nozzle is also an important factor. Venturi nozzles are generally preferred to the parallel bore nozzles formerly used, as they last longer, give higher grit velocity at more economic air consumption, and result in an overall increase in blasting efficiency. For many years, all nozzles had a straight internal bore with a small throat opening. The straight nozzles have an outlet abrasive velocity of about 217 miles per hour, 349 kilometers per hour, or 315 feet per second. In addition, they tend to spread the abrasive in a large blast pattern, with more concentration in the center and less at the edges. In 1954, the Venturi shape was developed. The new shape has a large entrance throat, tapers gradually into a short straight section in the middle, and then flares at the outlet end. The Venturi shape allows for abrasive velocity up to 450 miles per hour, 720 kilometers per hour, 660 feet per second, and an almost equal impact over the entire surface. Venturi is the most effective nozzle shape for tough cleaning jobs. Periodically, the user should check nozzle type. The Venturi type provides a higher abrasive velocity than a straight barrel type of the same size. Check for cracked and worn nozzles. A cracked nozzle should not be used because it can create a severe safety hazard. A worn nozzle decreases the effectiveness of the blasting operation. A nozzle orifice gauge is used to measure wear. Some users specify that wear of the nozzle should not exceed one nozzle number. In the United States, 1/16 of an inch, 1.6 millimeters. Other users may require that a nozzle be replaced when wear reaches 50% of the original size. The nozzle aperture test is described below. A test for nozzle pressure of the optimum 90 psi to 100 psi, 6.2 to 6.9 MPa, should be made using the hypodermic needle pressure gauge during the blasting operation. With the blaster's agreement, the inspector or operator should measure the pressure by inserting the needle into the hose as close as possible behind the blast nozzle when the hose is in actual use, blasting with abrasive. Materials for nozzle lining must be tough and durable and resist the abrasion which inevitably occurs. Nozzles lined with tungsten carbide have a 300-hour life. However, life expectancy is shortened when this nozzle is used with aluminium oxide or silicon abrasives. A silicon carbide nozzle weighs 42% less than a tungsten carbide nozzle, making it easier to hold for a long time. With a dependable abrasive, the silicon carbide nozzle lasts up to 500 hours, which is 50% to 60% longer than tungsten carbide. Norbide is the most durable lining, with a 750-hour to 1,000-hour life. It can be used with all abrasives. Although boron carbide nozzles are 2 to 3 times more expensive than silicon and tungsten, their long life makes them cost-effective. Nozzle size affects the type of work to be done, the volume of compressed air available, the amount of pressure available, and the type of blast unit being used. Longer nozzles result in more velocity and a more concentrated blast pattern, so they are preferable on tough cleaning jobs. However, use of a nozzle too large for the work may result in power being wasted by undue blasting. Nozzles should not be used as hammers, used for tapping signals from inside tanks or dropped to the ground. They should be checked regularly for cracks and wear. Nozzle aperture should be checked regularly by means of a nozzle gauge. In performing this test, first, a mark is made on the gauge using a grease pencil at the approximate size of the nozzle. Next, the gauge is inserted in the back of the nozzle and twisted one full turn, 360 degrees. Then, the gauge is withdrawn and the black mark examined. The ID of the nozzle is indicated by where the grease pencil is rubbed off. At the orifice size measured, the gauge indicates the volume of air in cubic feet per minute, or cubic meters per minute, necessary to deliver 100 psi, 6.9 MPa at the nozzle. For example, a single number 6 nozzle, 3/8 of an inch ID, 9.5 millimeters, would require a compressor supplying 196 CFM, 5.5 cubic meters per minute, to deliver and maintain 100 psi. If a larger diameter nozzle is used, or if the nozzle has worn to a half-inch ID, 12.5 millimeters, it would require a larger compressor supplying 335 CFM, 9.46 cubic meters per minute, to maintain 100 psi. The needle gauge is used to measure the air pressure at the nozzle. A hypodermic needle is inserted into the blast hose just behind the nozzle while the blast unit is in operation. If the pressure is less than expected or desired, the items shown here should be checked. The inspector should check for evidence of damage or sharp bends in the lines. Heavy objects should never be allowed to rest on a hose. Ensure couplings are wired together or securely coupled for safe operations. And ensure abrasive hoses are properly grounded. The condition of the material to be blasted significantly influences both the rate at which blasting can be done and the quality of blast finish obtained. Heavy rusted or corrosion-pitted steel is difficult to clean thoroughly because of the extra blasting time and attention necessary to remove deep-seated scale and injurious corrosion products. Somewhat heavier grades of grit and high blasting pressures are advantageous for such surfaces. Certain heat-treated alloy steels also acquire a particularly tenacious oxide scale, again requiring heavier grit and high blasting pressures for most efficient cleaning. In general, air pressure for grit blasting depends on such factors as grit quality and grade, type of material being blasted, and overall production requirements. Expendable abrasives are better used at high pressures, above 90 psi, 6.2 bar, to obtain maximum cleaning rates, as grit breakdown after impact is of little consequence other than creating something of a dust problem. Increased pressure materially increases rates of blast cleaning due to greater grit throughputs and higher particle velocities. Labor costs per areas blasted can therefore be considerably reduced, although grit losses tend to increase significantly above about 70 to 75 psi. Also, at high blasting pressures, above 90 psi, operator fatigue can limit productivity on long blasting shifts. Nevertheless, it is usually recommended that blast pressure as measured at the nozzle be kept as high as possible, with the provision that it cannot normally exceed 100 psi for safety regulations. work done is directly proportional to the air pressure at the nozzle. So, for example, at 60 psi nozzle pressure, only half of the area would be cleaned compared to the area cleaned in the same time at 100 psi. The main reasons for inability to maintain high nozzle pressures are inadequate air supply. Theoretically, a number 6 3/8 inch nozzle, one of the popular sizes, requires 196 CFM. To provide the necessary quantity of air, a compressor of at least 300 CFM would normally be employed. For a larger nozzle, more air would be required, and a proportionately bigger compressor would be needed. Too small air hoses. Friction losses are expensive. Internal blast hose couplings can cause loss of efficiency, up to 15% of the working pressure. External couplings and nozzle holders are a must. Badly designed machines may have a significant pressure loss through the machine. Too small piping on the machine again causes friction losses. And compressed air lines should be kept straight and as short as possible. Other important factors affecting blasting performances are correct choice of nozzles. Venturi nozzles are much more efficient than straight bore nozzles. Air must be clean and dry. Rates of cleaning cannot be quoted definitely. There are many variables affecting a blasting operation, including those shown here. As a very general guide only, high cleaning rates can reach 30 square meters per hour, 300 square feet per hour. Low rates can fall to as low as 4 square meters per hour, 40 square feet per hour. It must be stressed that these production rates are indications only and cannot be assumed for any specific job. Similarly, the consumption of abrasive can be variable, and calculation of quantities used is very much a matter of trial or experience. As a general guide, a consumption of 50 kilos of expendable abrasive per square meter, 10 pounds per square foot, is common for irregular structures. The degree of surface roughness and the rate of cleaning depend primarily on the characteristics of the abrasive grit used. Although the blasting abrasives in general use range widely from crushed walnut shells, glass and crushed slags to various metallic shots and grits, and even ceramic grits, there is a limited number of types of abrasive commonly used for preparation for painting. These are chilled iron grit or shot abrasives, crushed slag, naturally occurring mineral grit, ceramic grit. Despite the widespread use of the term sand blasting, sand is not listed as a grit blasting abrasive. Sharp sand is a cheap and effective abrasive, but increasingly cannot be used throughout the world due to the very real health hazard of silicosis. Some naturally occurring forms of sand are said to be silica-free, and these may still be found in common use, particularly in the USA. silica-free sand does not release silica in a harmful form, i.e. free silica, when it breaks up under the impact of the blasting process. Permission to use sand may occasionally be given for site work in the open air, but only when the operators and other personnel are carefully protected from the dust created, and the site and blasting conditions are approved by the health authorities, for example, Factory Inspector, OSHA. This is most likely to occur when the sand is to be used in conjunction with water jetting equipment. This is by far the most widely used abrasive for surface preparation in a coatings application facility or any similar workshop environment. Chilled iron grit is available in a variety of grades and to a specific minimum hardness. It is an excellent general-purpose abrasive due to its relatively high density, which gives high particle energy, and its slow but effective rate of breakdown, which maintains cutting edges on the grit particles. While chilled iron grit is used extensively for grit blast preparation in works or on-site where grit reclamation and recirculation can be achieved, it is too expensive an abrasive to be used where grit reclamation is not possible, as on many site jobs. Crushed slags from metallurgical processes have been made available as relatively cheap expendable abrasives. Copper slag, coal slag and aluminium slag are common. While quite effective grits for once-only use, by reason of their rapid breakdown to dust, they are not generally suitable for grit reclamation and reuse. These materials are often called expendable abrasives. These are relatively expensive grits, but their use can sometimes be justified by their special properties. Due to the retention of sharp cutting edges on the particles in use, their cutting action can be particularly effective, especially on hard base materials, which may resist effective blasting by chilled cast iron grit. Additionally, the effective cutting action can be achieved at blasting pressures lower than normally employed for other abrasives. These ceramic grits are particularly well suited to blast preparation of thin metal surfaces, which show buckling or distortion if blasted with chilled iron grit at conventional blast pressures. Finally, as these ceramic grits are essentially inert to normal corrosive influences, they can be safely used to grit blast stainless steel or non-ferrous material surfaces without causing rust staining, discoloration, or bimetallic corrosion. Types of blasting abrasive that are rounded in shape are known as shot. Their common use during the development of blast cleaning techniques leads to the common misuse of the term shot blasting. Shot used for blast cleaning has less cutting effect and hence will prolong the life of blasting equipment and machinery. For example, wheel abrators and other automated equipment. The disadvantage is that less cutting effect gives a more rounded, less rough surface, often below the adhesion requirements of today's high-performance coatings. It is still widely used in blast cleaning machines used to prepare steel prior to fabrication. The pre-fabrication primers used must be carefully selected, and must be compatible with the surface produced by shot blast cleaning and with the subsequent coatings if they are to remain on the steel surface and become part of the coating system. In addition to blast cleaning, shot blasting may usefully work harden a metal surface by peening, a process which can reduce the incidence of stress corrosion cracking. A typical analysis of copper slag abrasive may show the chemical content to be similar to that shown here. Notice that there is very little copper content, since the slag is a byproduct of the copper extraction process. Notice also that most of the contents are oxides of one metal or another. The inspector and the operator should ensure that both the type and size of abrasive being used is as specified, that the appropriate specified recycling procedure is followed. Most metallic abrasives, such as iron and steel shot and grit, and expensive abrasives, such as glass beads, may be recycled. Contaminants, including fines, dust, paint and mill scale, must be removed from the abrasive materials if they are to be recycled. Abrasives must be clean and free of moisture. They should be stored off the ground, away from moisture and the elements. Abrasives can be tested for cleanliness through use of a simple test known as the vial test. Some of the abrasive is dropped into a small vial of water of known pH, preferably distilled or deionized water, pH 7, and shaken. Typically, the ratio should be 1 volume of abrasive to 2 volumes of water. The top of the water is inspected for a film of grease or oil. The water can be visually checked for turbidity, cloudiness due to sediment, which is usually a sign of excess dirt, dust or clay in the abrasive. A litmus or pH paper test of the water in the vial will tell whether the abrasive is acid or alkaline. pH paper will indicate the actual value of acidity or alkalinity. If the abrasive is dirty or is acid or alkaline, the coating inspector should document these results and immediately report to the owner's representative. Litmus and pH paper indicates the presence of those chemical salts dissolved in water which form an acidic or basic solution. Note, litmus and pH paper will not detect the presence of the chlorides. If the red litmus paper changes to a blue color, the solution is basic. If the blue litmus paper changes to red, the solution is acidic. If, however, litmus paper does not change, it indicates the solution is neutral. However, even if the solution is neutral, it does not indicate the absence of soluble chemical salts, because some chemical salts, such as sodium chloride, common sea salt, form a near-neutral solution. Specific test papers may indicate the presence of soluble chemical salts. ASTM C136 is the test method for sieve analysis of fine and coarse aggregates. Typically, a 1 kilogram representative sample of abrasive is put through a series of screens, such as 1240 or 1640, and the percentage retained on each screen size is recorded. This test enables the inspector to compare the particle size and distribution of the abrasive with the data furnished by the abrasive supplier. Each type of abrasive is generally available in more than one size. Abrasives are graded according to how fine a mesh or sieve screen they can pass through without one particle of abrasive remaining on the mesh. When in doubt about whether a given abrasive is the correct size, a mesh or sieve test may be performed. Equipment required for the test includes an accurate balance, a set of NBS screens. A convenient quantity of abrasive is weighed. 1,000 grams is a very handy weight, and then poured into the top of the nested screens. The screens are nested so that the screen with the largest openings is on top, graded down through the screen with the smallest openings on the bottom. For example, from top to bottom, number 8, number 15, number 16, number 40, number 50, and so on. The screens are shaken over a retaining pan. The abrasive particles are retained on the screens, which sizes are just smaller than the abrasive particle. The finest abrasive particles pass all the way through and are caught on the pan. The next step is to weigh the particles which remained on each screen and calculate the percentage retained. This is why using 1,000 grams of abrasives to start with is convenient. If, for example, 238 grams of abrasives is retained at a given level, we know that 23.8% of the abrasive was retained at that level without doing a lot of extensive arithmetic. In addition to the specific size of abrasive, hardness is also a significant factor. Harder abrasives have more cutting effect, but may also shatter on impact, limiting their ability to be recycled. Softer abrasives have less cutting effect and may become rounded as they are used, but recycling is an economic advantage of such materials. Hardness is commonly measured on the Rockwell scale. For example, metallic chilled iron grit, HRC range 50 to 55, or on the MOHS scale, for example, copper slag abrasive, hardness range 6 to 7 MOHS. These two scales may be correlated, but manufacturers typically quote one or the other scale, not both. The following types of abrasive are generally available. In addition to the other abrasives we've discussed, the agricultural abrasives are commonly used in a variety of situations where abrasive dust associated with other abrasives may be harmful to sensitive equipment. When stainless steel or other high-purity alloys are blasted, it is important that the abrasive cannot embed metallic particles in the surface. Crushed walnut shells have been used, for example, to blast clean components of the Space Shuttle to preserve the integrity of the special alloy materials. This class of abrasives includes water slurries of abrasives that have low hardness and are soluble in water. It has been reported that sodium chloride, salt, and other products of that type have been used. Some or all of the items listed here should be taken into account when a blasting abrasive is selected. Recycling is usually done so that expensive abrasives, such as high-grade metallics, can be reused. It may also be used to reclaim less expensive abrasives, like sand, if shipping costs are a factor. The quality of the recycled material is critical. In centrifugal blasting, reclamation or recycling is a standard operation. The process is more difficult in nozzle blast operations, which are not confined. In small cabinets and blast rooms, recycling is fairly simple. It is more complex in larger rooms. There are four major methods of reclamation. Screen method. In this method, the abrasive runs over a series of screens. The top, large-size screen eliminates oversized materials. The remaining abrasive falls down to a smaller screen. Dust and fines pass through, leaving only usable abrasive in the screen. The method can be done by hand or mechanically. Air screen wash. In this separating system, the oversized abrasives are removed by mechanical screens. The abrasive is distributed over a wide sloping plate, which causes it to fall over the edge. As it falls, the abrasive passes through an airstream at a predetermined velocity. The usable, heavy abrasive is carried a short distance and then falls into a chute. This method is considered less precise than the screen method. Water method. Because it uses water, this method is used with non-corrodable materials only, never with iron and steel. In this method, abrasives are passed through a water wash, which separates the dust and fines from coarse particles. The upward velocity of the water is reduced, which causes the heavier abrasives to be deposited in the bottom of the reclaimer. The remaining abrasives are dried in a kiln before being reused. The water method is inexpensive and is helpful in reducing dust, but can require large amounts of water that should be filtered and purified before being released into drains or rivers. Cyclone method. In this separating method, the abrasive is drawn through a hose into a cylinder similar to a high-power vacuum sweeper. Rapidly moving air in the cylinder sends the dust and fines out the top of the cylinder. The heavier, reusable materials fall through a screen at the bottom. Testing should be conducted if abrasives are being recycled, abrasives such as river or beach sand are being used, There is some reason to suspect incorrect sizing or contamination of the abrasives. There is much variation in profile depth. There is an unexplained difference in color of the blasted steel. For the safety and comfort of the blast cleaning operator, it is essential that good quality working clothes are used. Typically, these would include safety boots with steel insert toe cap, coveralls, strong leather gloves, air-fed blasting helmet, incorporating a replaceable visor and leather cape. It is important that the operator has a good supply of clean, fresh air for breathing. Two common ways of achieving this are: a supply of air at low pressure is delivered from the blast pot via a filter. This method has the disadvantage of the air being the same quality, often poor quality, as that used for blasting. A separate supply of air, also at relatively low pressure, is fed from a remote air-driven pump well away from any contaminated or dust-laden atmosphere. Abrasive blast cleaning at high pressure is a dangerous operation. It is essential that steps are taken to protect both the operators and any spectators or other site personnel. Some considerations would be: no one but the operator should be allowed within the vicinity of the blast cleaning operation. Warning notices should be displayed. A lookout or potman should be on the alert. All equipment should be tested for safety in operation. A dead man's handle cutout device should be fitted and used. A dead man remote control valve, which allows the machine to be controlled at the nozzle by the operator, should be part of this unit. The inspector should ensure that this safety feature is always operable and is in use during blast operations. Several accessories are commonly used with the blast pressure pot, including abrasive metering valve, which meters the proper balance of abrasive to the air flow and nozzle size. Remote control or dead man valve. The remote control valve must be held in the closed position to pressurize and therefore activate the blast pot. When the valve is released, the blast machine is shut down, thus safeguarding the operator. If the operator becomes ill, faints or trips and drops the hose, he or she is not in danger of being hit by flying abrasives or the blast hose whipping around in the work area. The dead man valve could be considered to be cost-effective because it can eliminate the need for a pot tender or blaster's helper. Remote control valves may be operated by compressed air or electricity. Compressed air operated valves do not require any other power source than the compressor, but may be slow to react, particularly when the blast hoses and nozzle are a significant distance from the blast pot. Electrically operated valves operate instantaneously, but require a power source and are not intrinsically safe so cannot be used in a hazardous environment. Filtered and regulated air-supplied respirators are required for all dry abrasive blast cleaning. Not only the operator, but all personnel in the contaminated area must wear approved breathing apparatus. In addition, all equipment must be grounded to prevent electrical shock. All participants in the surface preparation process, including coating inspectors, should use common sense in detecting potential hazards. Any lighting, scaffolding or equipment malfunctions presenting safety hazards should be reported to the appropriate person. Knowledgeable and responsible workers will always assure themselves of the safety of staging, spiders or swing scaffolding before using them for work or for inspection. Never get into the path of an abrasive blast. The abrasive particles can be traveling as fast as 450 miles per hour, having the effect of a shotgun blast. The coating inspector must follow all safety and health rules as established by the safety engineer or the person responsible for safety on the contract. The coating inspector should be familiar with, and when appropriate, make use of the following protective equipment: hoods, respirators, heavy protective clothing and gloves. The operators may be required to ground equipment, and the coating inspector may be required to verify that the equipment is properly grounded. Site safety must conform to applicable worker protection rules and regulations. In the USA, OSHA, Occupational Safety and Health Administration regulations provide the necessary guidelines. In other countries, similar governmental bodies have developed similar regulations that must be observed. A more detailed appraisal of appropriate regulations is provided in the safety module of this program. When blast cleaning is taking place, it is common that some areas should not be blasted for a variety of reasons. Typical examples include surfaces that are already painted or sensitive equipment such as valves or instruments. Where such surfaces have to be left unblasted, these can be masked off using suitable templates of metal or rubber, or suitably tough masking tapes firmly secured to the surface, requiring protection from the blast stream. Masking materials should be fixed in place before any blast cleaning begins in the immediate area. They should be checked on a regular basis to ensure that they are providing adequate protection, and should be carefully removed at the completion of the blasting and painting operation. On completion of blast cleaning, the blasted surface should be cleaned to remove residual dust and abrasive. It may be blown down with a high-pressure jet of clean dry air, vacuum cleaned or brushed with a clean dry brush until there are no traces of residual dust or grit. The surface at this point in time should closely resemble the visual standard of surface finish that was specified. For example, NACE number 2, SA 2.5, etc. When dust or grit is not completely removed, it often remains hidden in crevices or corners. It can be disturbed by the high pressures of the paint spray stream and can be distributed into the paint film, causing a poorly adherent paint layer or an incomplete film. In addition to achieving cleanliness, abrasive blasting alters the substrate from a more or less smooth surface to a uniformly textured surface. This textured surface is the result of the sharp abrasive particles striking the steel at high speed and leaving small impact craters or irregularities. This texture is called surface profile or anchor pattern. A well-written coating specification will call for a range of surface profile depth, expressed either in mils or microns. For example, the specification may call for a surface profile of 1.5 to 3.5 mil, 37 to 87 microns. Surface profile is important in that it increases the surface area and roughness, anchor tooth, to which the coating can adhere. Too shallow a surface profile may result in premature coating failure due to lack of adhesion, seen as peeling, blistering or delamination. In general, the greater the surface profile, the better coating adhesion will be. One exception to this rule appears to be inorganic zinc silicate primers, which tend to split, lose cohesion, when the anchor profile exceeds about 2.5 mils, 67 microns. This effect may be in part caused by attempts to increase the thickness to achieve coverage of the profile peaks. Inorganic zinc silicate primers are well known to be sensitive to excess thickness. The guidelines provided by the coating manufacturer on technical data sheets should be followed. The depth of surface profile can be evaluated by several methods shown here. Examples of surface profile coupons are available in 0.5 mil, 12 micron increments from half a mil to 3 mils, 12 to 75 microns. The coupons allow for determination of surface profile through comparison. The Keen-Tater surface profile comparator consists of a reference disc and a 5-power illuminated magnifier. The disc has 5 separate leaves, each of which is assigned a number representative of the profile depth of the leaf. The reference disc is compared with the surface through the 5-power magnifier. The leaf that most closely approximates the roughness of the surface is considered to be the pattern of that surface. Reference discs are available for sand, grit, steel, or shot abrasives. Surface profile may be measured with replica tape, a proprietary product produced by the Testex Corporation. 2 types of tape are commonly used: coarse for 0.8 to 2 mil, 20 to 50 microns surface profile, and extra coarse for 1.5 to 4.5 mil, 37 to 112 microns surface profile. A piece of tape with a small square of compressible foam plastic attached to a non-compressible plastic mylar film is applied to the blast clean surface dull side down. A hard, rounded object, burnishing tool, such as a swizzle stick, is then used to crush the foam to the blast clean surface, causing the foam to form an exact reverse impression replica of the actual surface profile. The tape is removed from the surface and an anvil micrometer is used to measure the thickness of the foam and the plastic. The thickness of the mylar film, 2 mils, 50 microns, is subtracted from the micrometer reading, and the result is the depth of the surface profile. The base of the instrument rests on the tops of the peaks of the surface profile, while the spring-loaded top projects into the valleys. Method of use is according to ASTM D441791, Method B. This is a very sensitive test, and although it can be used in the field, its best application is in the laboratory. Other surface profile instruments, such as a depth measuring microscope or diamond point tracking stylus gauges, are sophisticated laboratory methods not commonly used in the field, on-site or blast shop. Surfaces must be free of oil and grease before blast cleaning. Blast cleaning will not remove oil and grease. All surfaces should be inspected after cleaning for compliance with the specification. Cleanliness after preparation is important. Residual traces of abrasive must be blown off, vacuumed or swept away before primer coating. Note, if lead is present in the paint waste or blast debris, the surface cannot be blown off. Contractor must follow all regulations regarding lead removal. Any scaffolding, staging or support steel above the surface must also be cleaned to avoid abrasive from dropping onto the freshly cleaned surface or onto the newly primed surface. Surfaces prepared for coating should not be allowed to deteriorate or to be contaminated in any way between grit blasting and spraying. Clean, grit-blasted surfaces should not be handled or touched unless hands are protected with clean gloves. They should also not be exposed for prolonged periods or exposed at all to atmospheric or storage conditions of high humidity, as under such conditions oxidation and rusting may proceed very rapidly. As far as practicable, any storage after blast cleaning should be in a warm, dry environment, and ideally, spraying should follow blasting as quickly as possible. Commonly applied rules indicate a maximum delay of 4 hours and require that if visible deterioration has occurred, the surface preparation shall be repeated. There are many standards related to surface preparation issued by many standards writing organizations. The ones that will be described in some detail in this module are produced by NACE International, formerly the National Association of Corrosion Engineers; SSPC, the Coating Society, formerly the Steel Structures Painting Council; ISO, International Organization for Standardization. The relevant standards will be discussed as they relate to the specific surface preparation method at hand. Ambient conditions may have an effect on the abrasive blasting process, as well as on the blast cleaned surface before painting. Ambient conditions include air temperature and substrate temperature, relative humidity, dew point temperature, environmental exposure, for example, marine and industrial. It is unwise to abrasive blast if the steel surface is much colder than the surrounding air. Moisture may condense on the blasted surface, causing the surface to flash rust. The substrate temperature may be checked using a steel surface thermometer. When blast cleaning, high humidity, moisture, can result in rapid deterioration of the cleaned surface. Final dry abrasive blasting should not be performed in wet or damp conditions, that is, when raining or when the relative humidity is very high, generally greater than 90%. Relative humidity is defined as the amount of moisture, water vapor, in air compared with the maximum possible in the air, i.e. saturation level. If RH reaches 100%, then the air will not support any more water vapor, and a surplus would appear as condensation. For that reason, most coating specifications have a requirement that coating is not carried out if RH exceeds a certain limit, usually 85 or 90%. In addition, if air is saturated with water vapor, the evaporation of solvents is inhibited, causing problems with coating film formation. For this reason, coating specifications normally have a requirement that coatings should not be applied if the temperature of the steel or the surrounding air is less than 3 degrees centigrade, 5 degrees Fahrenheit, above dew point. Relative humidity and dew point are both calculated by making temperature measurements with a hygrometer. Dew point is defined as the temperature at which condensation occurs. If the ambient temperature falls below dew point, or if some or all of the structure has a temperature below dew point, then condensation will occur. Coatings applied over a wet surface will generally not achieve adequate adhesion to the substrate. If abrasive blasting is performed when environmental conditions are close to the dew point temperature, condensation is likely, and flash rusting may occur. The relative humidity and the dew point can be determined using a sling psychrometer and psychometric charts, which are discussed in the inspection module of this program. To reduce the risk of a prepared surface deteriorating before coating, specifications often impose a time limit. Typical wording may be, coating shall be applied to surfaces prepared for painting within 4 hours of completion of the preparation activity. Clearly, the risk of deterioration depends to a large extent on prevailing ambient conditions, temperature, relative humidity, etc. So the 4-hour period allowed may appear to be arbitrary. It is imposed as a helpful safeguard and should be observed when specified. Other typical time allowances may be 2 hours for the most critical applications or in changeable weather zones, or 6 hours or even 8 hours when stable, positive weather conditions can be anticipated. The specification statement may be developed by the addition of or before any visible deterioration of the surface, whichever is the sooner. In this case, the time limit still applies. If surface discoloration is seen, the discoloration should be removed by further preparation and the surface coated, regardless of how much time has passed since preparation was completed. One way to ensure that ambient conditions are suitable for painting is to dehumidify the air. This is naturally only possible in an enclosed space. A dehumidifier works by drawing ambient air across a desiccant, such as silica gel, and delivering the air at a lower RH to the desired space. A separate stream of air is heated and passed over the desiccant to remove the moisture and revitalize it. This second stream of air is vented to the atmosphere. The attainment of very low humidity is possible in large spaces. This technique is commonly used in ships' tanks and crude oil storage tanks. Other types of dehumidification equipment are available, and these are discussed in the Advanced Surface Preparation module of this program. In marine and industrial environments, where the air contains particles of chemical salts, the possibility exists that these salts may deposit on the workpiece. If this occurs after blast cleaning but before coating, it may be necessary to wash and re-blast the surface. The presence of certain chemical salt deposits, such as ferrous sulfate or ferrous hydroxides, may be determined by means of test papers or chemical test kits. Generally, corroded steel is more difficult to clean than new steel. The surface is less smooth than new steel, and it often contains chemical contaminants bonded to the steel in the corrosion process. These contaminants are known as soluble salts and are not easily removed in the surface preparation process. Steel that has been exposed to corrosion in the presence of certain contamination, for example sulfates and chlorides, may be difficult to adequately clean. Even though the surface may appear to be properly blast cleaned and free of corrosion products, it may contain enough non-visible contamination to create a surface unsuitable for coating. In extreme cases, heavily contaminated areas will, after blasting, absorb moisture from the air, turn dark and rapidly deteriorate. This effect can sometimes be seen within minutes of completion of the blast cleaning process, particularly when humidity is relatively high. It is a clear indication that the surface is still contaminated. To remedy the problem, the surface should be cleaned more thoroughly. Further blast cleaning may be effective in some cases, but better success may be achieved by washing using high-pressure wash equipment. Water jetting may also be effective to remove heavy contamination. Surface preparation in these cases should be followed by testing for soluble iron, ferrous salts, and/or chlorides, to ensure that remaining contamination is below critical levels. The rust which forms on steel surfaces exposed to either industrial or marine atmospheres may contain significant quantities of sulfate and chlorides. If these compounds are not removed, they can give rise to premature paint failure. Spot tests have been developed to detect the presence of soluble iron, sulfates and chlorides on blast-cleaned steel. In these spot tests, color reactions are used to indicate the sites of contaminated rust. Each method employs pieces of chemically treated filter paper which can be dried after use to provide permanent records. The papers are pressed against the steel surface which has been wetted with distilled water. After a short time in contact with the surface, the papers are removed and examined for color changes.